Move on to the next speaker. So next up is Adam Iaizzi from who's currently at the AAAS Science and Technology, being a Science and Technology Policy Fellow at the U.S. Department of Energy. Thanks for joining us.
Hello. So, okay. Let's see if I did this right. Okay. So
I can hear you. We're good.
Okay, great. I'm still not confident that I know how to use Zoom. So my name is Adam Iaizzi. I'm currently a AAAS Science and Technology Policy Fellow at the DOE Office of High Energy Physics. My previous life, I was a computational condensed matter theorist. And so this is work that has nothing to do with what I'm doing at DOE. And in fact, there's a little disclaimer at the bottom of my slides, but just to be 100% clear, nothing I say here is, all these are my opinions, and none of these things are representing the DOE or AAAS or the US government. That's important for them to know that I said that. Okay, so I'm here to talk about field-induced freezing in the unfrustrated Ising antiferromagnet, a title I wrote before I realized how hard it is to say. Perhaps a better title is Stable Frozen States Without Disorder, because it's easier to say. So I'm going to be interested in the 2D Ising antiferromagnet. Probably most people here know this already. Square lattice with periodic boundary conditions. Before you add the field, this is basically the simplest model that has a non-trivial phase transition. Without the field, you can there's a one-to-one mapping onto the ferromagnet. But the reason you add the field is it destroys that mapping. So you no longer now this is different from the ferromagnet. I mean, you can also add a staggered field to the ferromagnet, and so you can predict pretty easily what you'd expect the behavior to be at zero temperature. So you add magnetic field, and you're stuck in this antiferromagnetic ground state until it jumps to saturated. And now you can imagine I probably didn't show you that figure because that's what's going to happen. So for dynamics, I'm going to use basically the simplest possible dynamics, Metropolis, Monte Carlo with single spin flip updates. If you've ever written a Monte Carlo program, this is probably the one you wrote. And I'm going to do a quench, which means you start from a infinite temperature state, which is a totally random spin state. And you do an instantaneous quench to some temperature T. And this sounds fancy, but of course, this is really just what you do if you're not trying to do anything else. So if you just make the simplest version of the simulation, that's a quench, because you're going to start with a random spin state and do updates. So what happens? And again, the hint is it's not going to be this. So at high temperature, here's with inverse temperature. So beta equals 2, that's pretty close to the a higher temperature limit. That blue line shows that it kind of looks like what you'd expect from that other figure, plus with some finite temperature rounding. But as you get to lower temperatures, these really weird plateaus show up. And so there's a few interesting things about these plateaus. One is that they're metastable states, like they're not the ground state, but they're completely stable. So you can add up, once you're in the center of these plateaus, you're not near those edges, in the flat part. You can add up the probability of flipping all the spins, and it even for pretty modest temperatures, you'll quickly end up in the running out of numerical precision to specify basically the zero probability. And here I've added no intrinsic disorder, right? This is still a regular antiferromagnet with a field. There's no random fields, there's no random interactions, anything like that. It's just the quench disorder. And then the other feature here is that you have these valleys of ergodicity, which is my term. There might be, you could disagree with what I call them, between the plateaus, where it seems to converge to the true ground state. And I can confirm, you can't see it on this graph, but it does converge to the correct ground state. So I should say that I made this figure especially for talks because it's easier to see on slides, but there's a much nicer version of this in my paper. And then the other thing is the boundaries and the sizes are pretty much unimportant. So once you get above even a pretty small system, so I think like 30 by 30 is overkill, essentially. Like you're already at essentially the ambient behavior. So, okay, so from now on, we're just going to talk about zero temperature, and I'm just going to focus around the centers of the plateaus because that's the first thing we decided to do. So you can work out what the zero temperature, like the results of a quench to zero temperature are, and there's just this sort of stepwise function, and you get ergodicity of those special points. And yeah, for now I'm talking about zero temperature. So what's happening here? And so I have these two little movies which I've tested and I hope will work. So what you're going to see on the left is you're right in the middle of that first plateau. Start from a random state and watch the. So I'm just going to show when the spin changes. It's not going to be real time, and so there's pluses and minuses for the local spins, and then the background shading is, which I'm hoping you can see. The background shading is which antiferromagnetic domain you're in. And so you can see you start flipping spins, and you actually don't have to go very long, and now you're stuck, and it'll stay here forever until obviously the animation loops. So it doesn't always look like this, but it looks something like that, and so this happens very quickly. Like basically, order L squared updates, you are in one of these frozen states, and certainly a few times that you're almost always in one of these frozen states. So what's actually going on here is that, so the nice thing about these very simple updates is that you can just look at them and sort of diagram them out. So since you only update the local spins, they only one spin at a time, and they only interact with their neighbors. There's only 10 possible configurations that you really have to worry about, and because you can only flip the center spin, there's only 5 pairs of these that you have to think about. And basically, what happens is most of these pairs will have, one of them will be a lower energy. So if you, using the Metropolis algorithm, if you arrive there, you will always accept that. And so at h equals 0, the only pair that you can flip back and forth, which we call reversible update, is the one where you have 2 up neighbors, 2 down neighbors, because that's degenerate whether your middle spin is up or down. And then once you break that, you have none of these reversible updates. And so I've got a little ahead of myself. What happens is you get one of those reversible updates back when you get to h equals 2, because then you are now this second row, or this row here, now you can flip these back and forth, no change in energy, and that's when you get the value of ergodicity. You can probably imagine where I'm going with this. A similar thing happens for this one with the all up, although the case is a little different. And so the work I've done here is related to some of these older papers by Karpivsky and Redner and their various students, and Kipton Barron for one, and highly recommend you look at these papers. They're very nice. And so in the ferromagnet with no field, you can get stuck in a stable state. And it's basically, if you have a state where there's a domain wall that has horizontal or vertical wall, domain that has horizontal or vertical domain walls, that's totally stable under the dynamics. And then that's it, you get stuck there forever. And it turns out actually they've worked out, you can derive the probability of getting stuck in one of these striped states from a connection to critical percolation theory. It's exactly 0.3390 something. So here, most of the time, though, you still reach the ground state. And so for time, I'm not going to go into this in detail, but essentially something similar happens here, except now by getting rid of those updates that make it easy to move the corners of these domain walls around, you end up with basically a rapidly growing number of these states you can get stuck in, which means that you almost always pass through one of them before you get to the ground state, and then you get stuck there. And by almost always, I mean for any finite system, always. For any system of reasonable size, always. It's like it's very hard to get to the true ground state. The other point here is the corners here host the excess upspin. So the second plateau, basically similar, you can come up with a set of rules for what sorts of domain walls are stable. And once you reach one of those states, you're stuck there forever. And then the saturated case is a little more interesting because it actually doesn't freeze. Instead, you get this interesting vanishing temperature dependence, and you have a fluctuating coexistence of both antiferromagnetic ground states and the fully polarized state. I don't have time to talk about that more here because I want to make sure I leave some time for questions, but this also maps onto this thing called the hard squares problem. It's kind of another, basically a separate interesting thing. Okay, so here's a quick summary, and then I'll talk about hopefully to convince you why this is interesting. So we did quenches in the Ising antiferromagnet with the field. We found these stable plateaus, no disorder, and even within these plateaus, every single spin is unflippable. So if you tried to flip that spin, you'd raise the energy, which at zero temperature in these dynamics you're not allowed to do. And so then you can understand these plateau states in terms of these stable local configurations. Ergodicity gets restored when you have these delta E equals 0, or what I call reversible updates available. And an important point I want to raise here is that Monte Carlo dynamics aren't physical dynamics, right? Like in some sense, the Metropolis algorithm is like a bit misleading in that it seems very, like the single spin flips seem very plausible for how an actual material might behave. But we don't have to follow there's no physical rules here other than detailed balance. And so you can pick, and there are many like larger sort of update schemes like Wolf updates, Wolf algorithm, or the Swenson-Wang, where you're doing these plateau updates, and that choosing those dynamics affects how you'll get stuck. So if you did a different update scheme here, you wouldn't get stuck in these plateaus. You might find different plateaus, but you wouldn't find these ones. So why should we care? So one is Markov chain Monte Carlos might be the most widely used single algorithm, not just in physics, but beyond in many fields. Finding the ground state is an optimization problem in a high dimensional space. So, obviously physicists are interested in that. Things like spin glass, also protein folding, also machine learning. These are all, you're doing some sort of gradient descent or trying to find, trying to maximize some function. And when you think about optimizing some function, in some space, like in this case, it's a very high dimensional space, right? But like in general, you have a lot of parameters, and you might think of that as like, oh, I have some potential energy surface I'm trying to move around on. And that is a useful picture, but it can be kind of misleading because your dynamics don't have to obey the locality of that potential energy surface. And in fact, usually you pick dynamics that don't, because that's very helpful. It helps you explore the state faster. And when you change your dynamics, you actually change what are local minima, like what seems to be local minima to dynamics. So if you're just doing nearest neighbor hops in this space, then it's very easy to see what a local minimum is. But if are doing like loop algorithms or something, it can be much harder. And then the other interesting thing here is that so sticky and glassy problems like this are usually really slow, but this case is actually very fast. So you reach one of these frozen states almost immediately, and then essentially you can turn the simulation off. Obviously, I ran the simulations for a really long time to double check, but probably there's some follow-up questions here that you could do on a laptop, which is pretty cool, that you don't need, like super intense, computing resources to do this. And so that's all I have right now. And I just wanted to highlight, if you're interested in this, I think it's a fun problem. Also, if you think I did anything wrong, feel free to get in touch with me. If you scan this QR code, it will take you to, whether you can download the paper or the source code or anything else. And then one last thing is that APS is a forum for early career scientists. It's one of the units. You can join it for free. I highly recommend you do if you are a postdoc or a recent graduate or you're someone who cares about what happens to those people. It's a great community, and we're working on how we can help early career scientists, and especially now. So thank you very much.
Thanks, Adam. Thanks a lot. We had a couple of questions from Joshua Heath. I think one of them you answered, which is whether you'll get the plateaus in the Wolf algorithm. I think you alluded to the fact that's probably the case. The other question was whether... Yeah,
it depends, essentially.
Yeah, whether you...
it wouldn't be the same.
Whether you get valleys of ergodicity in the Heisenberg model.
Hang on. So I'd have to... So the problem... probably the answer is yes, but in some sense. But I can't say anything more specific than that without thinking about it more carefully. Because quantum Monte Carlo is then, an order more complicated than this. But that's a great question.
Great. Okay, we're gonna have to move on just in the interest
of time. Course.
Thanks so much for your